So let's get started. So as I promised, we'll see at least one application from lattices which we don't know how to do even in the pre-quantum setting from any number theoretic assumption. Okay, so there are a few very nice such applications that are there, but one which is a favorite of many of us is this idea of fully homomorphic encryption. I have talked about this before a little bit. Let's try to go into it in detail today. So the idea of a fully homomorphic encryption scheme is simply that you should be able to compute on encrypted data. Now, if we think about computing on encrypted data, this sounds very weird. At least if we reflect on it, why is it surprising that you should be able to compute when data is encrypted? That means that let me write it. Yeah. So what this means is that if I have CT1, CT2, let's say a bunch of CTs up to CTn, then homomorphism or being able to compute on encrypted data means that I should be able to run some algorithm on it. Okay, so I will represent my algorithm as some sort of big circuit. Okay, and I will get some output. Now this circuit could be anything. It could be some kind of machine learning algorithm, it could be some kind of genomic data processing algorithm, anything. It could be something as simple as computing the mean or standard deviation of your grades. It could be any circuit, right? And the idea of fully homomorphic encryption is that as the name suggests, right, the ciphertexts they satisfy a homomorphism. So intuitively what this means is that if CT1 encrypts x1, CT2 encrypts x2 and CTn encrypts xn, right, and I have some circuit, let me call it f, right, and ultimately I would like to compute f of x1 to xn, then I can actually compute I can compute f on the CTI themselves. Okay, and when I decrypt it, so suppose let us think for simplicity just about addition. So suppose I add up all the ciphertexts and then I decrypt this, then the guarantee that I get is that the decryption gives to me an addition of all the x's. Okay. Now, why is this surprising? Why do we not expect this to happen? Why should the idea of homomorphic encryption be surprising? So this indeed used to be a big open problem for a long time, and it was solved after almost 30 years of it being posed by Gentry. Okay. So yeah, the question I was asking is that why should we be surprised by homomorphism? It would be a real shame to just see the algebra and then walk away. Let us try to think about this question. Do I expect to be able to compute on data while it is encrypted? I mean, do I expect to be able to run algorithms on ciphertexts? Right. So, the answer is that encryption and function computation are generally not expected to be commutative. Yes, that is a technical answer, but intuitively speaking, the reason that this is quite surprising is because when I think of just general encryption, let us say public key, even symmetric key encryption, then the guarantee that a ciphertext gives me or an encryption scheme gives me is that the ciphertext looks like a random element. We have been seeing this, right? We have been seeing all these different schemes that we have seen. The guarantee that we have is that the ciphertext looks random. If the ciphertext looks random, this means that it hides the message, right? Because obviously if it looks random, then it leaks nothing about the message. So if it looks random, then you know, why should any kind of computation make any sense, right? This is the question. And I personally still find it very surprising that we can do this, and we will see that the scheme from learning with errors that we saw in last class, a variant of that itself allows us to get this. Okay. So, are there any questions? The customary application of this, you know, that we use to motivate this primitive is that, you know, you have some cloud. So, you know, so cloud here means like a Google or Amazon or something. So, some organization which has massive computing powers which you don't have, and you know, let's say that what you have is just your phone over here. Okay, and you would like to compute something on some input. So, you know, you have some input x, okay, and you would like to compute f of x. Now, you yourself do not have the computational resources to compute f on this data, right. So, what you could do is you could encrypt x and send it to this cloud. Okay. So, here x is obviously a vector. You could encrypt x and send it to this cloud. This cloud can compute enc of f of x for you, okay, and send it back. And then you can simply decrypt to recover f of x. All right. So, this is the idea. As usual, we'll approach it formally. So, what are the algorithms that a regular public key encryption scheme has? Key generation, encrypt and decrypt, right. Now, additionally we will have something called evaluation. So, this is a public key algorithm. So, it will take a bunch of ciphertext, it will take some input circuit and it will evaluate the circuit on the ciphertext. Okay. So, let's define these. So, homomorphic encryption. Okay, so you could you could have your usual algorithms which are, you know, key generation, right, which will take some 1 to the n and output a public key, a secret key. And now also, just to make the homomorphism explicit, we will also output a separate evaluation key. But this evaluation key is public. So, I mean, you could think of it as being part of the public key itself. Okay. So, the key generation will output this. Encrypt is as before. Okay. So, it takes the public key and some message m and it outputs a ciphertext. Okay, and decrypt is also as before. So, this is just going to take the secret key and some ciphertext and it will output some message. The new thing is that now there is an eval algorithm. Okay, so, this will take some function and some ciphertext. So, CT1 up to CTL, let us say. Okay, so, the arity of the function f is obviously L over here. Okay, so, it takes L inputs. For simplicity, we will think of it as being a Boolean function. So, it just outputs a bit. So, it takes L input bits and it outputs 1 bit. We'll think of it like that. So, this evaluation is going to take these ciphertext and this function and it's going to output, you know, some sort of new ciphertext. So it will compute on these input ciphertext and it will output some ciphertext which is supposed to have, you know, f of the inputs sitting inside it. Okay, we'll make that formal. So the algorithms are clear, right? So just keygen and enc dec as usual, and now there's an extra eval. Okay, good. So let's see. So you know, let's define homomorphism. So a scheme HE is L homomorphic if for any depth L arithmetic circuit F and any set of inputs M1 to ML, it holds that the probability that, what notation did I use? Okay, the probability that decrypt, right, which takes as input the secret key, and eval of F CT1 to CTL, comma the evaluation key, okay, is not equal to F of M1 to ML is negligible, where PK, SK and EVK are output by keygen and CTI is output by encrypt PK MI. So let's pass this definition, okay. So intuitively L homomorphism just means that it will support computation up to depth L, okay. So if your circuit is up to depth L, then it will support computation of that circuit on the ciphertext, right. And formally the way we write it is that, you know, when I decrypt this CTF, so previously we were calling this as CTF, right. So if I evaluate F on CT1 to CTL, I get some CTF, right. And if I decrypt this, then I should get F on the underlying messages with all but negligible probability, okay. Is it clear? Yeah. And I mean the rest of it is just that obviously this will hold only if the keys and the ciphertext are generated honestly, otherwise of course I have no control over what happens, yeah. Okay, good. So this is L homomorphism. And let us talk of compactness. So this is a very important property. So compactness basically means that when I evaluate this circuit on the ciphertext, the resultant ciphertext that I get should be small. It should be hopefully not much larger than the original ciphertext that I started out with, okay. So in particular it should not depend on the size of the circuit that I computed. Okay, so compactness, a homomorphic scheme is compact if ciphertext size is independent of the size of the evaluated function. Is that good? Okay, so it's again it's very natural. So I want my final ciphertext to be something short, independent of the size of the circuit. Okay, good. So now before I show you the scheme, I just want to talk about two two ideas that we will use in the scheme. So one is this lemma which is very useful in cryptography. It's called the leftover hash lemma. Okay, and even though this lemma is actually fairly general, I will only state a very small specific case of it which will suffice for us, and I will not even prove the lemma. So that is yeah. So the lemma is that in the form that we will use it, the lemma says the following. Okay, so if I sample a matrix A randomly from ZQ n by m, okay, where m is greater than 2n log q, okay, and I sample r from 0 1 to the m by m. So basically I have a fat matrix here A, okay, and I multiply it with a random binary matrix R, okay. Then AAR is indistinguishable from A uniform. Okay, and this is statistically, so this is not relying on any computational assumption. Very good, thanks for asking that. So the question is, what's the meaning of this notation A comma AR? It just means that if I give you A and A times R, to you this distribution is indistinguishable from A comma uniform of the appropriate size. Okay, and there's one more idea that we will need. Okay, so let me define bit decomposition. Okay, so let x, it's just what the name suggests. So let me write it down and then we'll see what it means. So if x is in ZQ to the n, okay, let W in 0 1 to the n log, okay, wait, let Wi in 0 1 be such that x can be written as summation I 0 to log q minus 1 2 to the Iwi mod q. Okay, so this is you know, everybody has seen this. Basically, it's just the binary expansion, okay, of x, the binary decomposition, and you know, we output W0 up to W log q minus 1. So, whatever are the coefficients of 2 to the I, we output that. So, we just decompose x into its binary, you know, its binary representation, and here note that if x is of length n, then what is the length of W? N log q, right. So, each, because every element will you know, become log q bits, right. So, yeah, let us ignore rounding for a second. So, if I have an element in ZQ and I want to make you know, I look at the binary representation, then obviously it is going to be log q bits. So, it will just follow from that. Okay. Now, I want to define one last thing before we see the scheme, and that is this matrix G. Okay. So, this is a very special matrix which we use quite a lot in these in many lattice based schemes. Okay. So, okay. So, let G transpose be 1, 2, 4 up to 2 to the k minus 1, where you know, 2 to the k minus 1 is greater than equal to q over 2. Okay. So, these are you know, the powers of 2. So, I start with 2 to the 0, then 2 to the 1, 2 to the 2, as far as I can go up to q. Okay. So, these are the powers of 2, and now I define a matrix G as you know, by stacking these G rows one after the other. Okay. So, G transpose. Okay. And this is in ZQ n times Nk. Okay. So, I mean, I am going to use G of appropriate dimensions depending on my scheme. Okay. So, basically right now all that we are saying is that let me think of n rows, and I will stack in each row, I will sort of stack these G's in this way. So, I will end up with Nk columns. Okay. Okay. So, this is our matrix G. Okay. So, this is like a powers of 2 matrix, it's even called that. So, this is a powers of 2 matrix, and you know, a very natural thing is that you know, if I take the inner product of a bit decomposed vector. So, if I apply bit decomposition to a vector, okay, and I take the inner product with the powers of 2 vector, right, then I should recover the original vector. This is just by definition of bit decomposition and powers of 2. We will write it in this matrix form. So, let me define this notation of G inverse. So, define G inverse as follows. So, here we are abusing notation. So, G inverse is not the matrix inverse of G. Okay. So, I am going to tell you exactly what it is, but I just want everyone to remember that we will continue to you know, abuse notation in this way. So, yeah, G inverse is actually going to be the bit decomposition function. That we saw before, but I will just write it more carefully here. So, this matrix G we already saw is like a powers of 2 matrix somehow, right, and we will define G inverse as a function such that G times G inverse of a vector just gives back the same vector. Okay. So, we are just going to abuse notation and write it like G inverse. So, the lemma that we can write here is that for any m greater than n log q, there exists a fixed efficiently computable matrix G and an efficiently computable function such that for any matrix M, okay, ZQn cross M prime, let us say G inverse M 0 1 nk cross M prime such that G times G inverse of M is simply M. Okay. So, note that what I am taking as input to G inverse is some matrix n by m prime. Okay. So, what I am doing is that when I apply G inverse to that, I simply take the bit decomposition of each entry of the matrix and write it down in column form. So, that is why there is a blow up of this k, right. So, k is log q, again ignoring rounding and so on. Okay. So, it makes sense, right, and now let's go back and remember what is G. So, G has as its rows the powers of 2, right. So, if I take G times G inverse of something, then the powers of 2 will the inner product will happen between the powers of 2 and the bit decomposition of a given entry, and these two will result in getting back the entry itself, right. So, if I apply G inverse of M and then I apply G to that, then naturally I should get back the same matrix. Okay. So, yeah, these were the two things that that we needed in order to proceed. So, is it clear? So, the first thing I showed was just this a very special case of the leftover hash lemma, which says that statistically speaking, if I give you a fat enough random matrix and I multiply that on the right with a random binary matrix of appropriate dimensions, then I get a uniformly random matrix. So, this is like saying that even though I give you A, this binary matrix R has sufficient entropy such that A times R gives me back something which is random. Okay. So, yeah, good. So, that these are the two things that we